But okay, sorry, got distracted by the recorded message. So let's look over what we'll be talking about. So I will briefly talk to you about Docker Build and how that ties into the BuildKit world in the future. We'll go through the demo, and then we'll dive deeper a bit into the implementation of how it works and discuss some of the challenges that I've encountered when trying to marry BuildKit and Buildpacks from both BuildKit side and Buildpack side. And I will also talk about potential additions and future work that can happen to this integration. And we'll have hopefully time at the end if anyone has any questions or for discussion if anyone is interested. So without further ado, let's jump in. So Docker Build, probably a lot of people on this call will be familiar with this one, but I just wanted to set the stage because it will be interesting to see how this solution has evolved into something like BuildKit. So if we look at the traditional Docker build, then the way you could think about it is pretty much in the following way. You have your Docker file, which is your cookbook, the instructions on how to turn your source code into a container image. And you have your context, which is usually your source code, but can be something else as well. Maybe it's a table or some binaries as well, maybe if you built something already. So as a result of that, you get the container image, and you can control the build behavior where various toggles. You can, for example, do things like change the network mode. You can also very commonly used feature is to change the behavior by injecting build args. So essentially that lets you do some form of templating of the Docker files where you could potentially change the base image or change how your container image is created. But obviously it's nothing nearly as powerful as something that BuildKit can offer or Buildpacks can offer. And if you're interested in more details, then there's Docker docs there, and I'll share the slide as well so you can explore after the fact more about how this works and what it is. If we look at BuildKit, basically we went from the fact that there was a single implementation inside the Docker daemon, which was responsible for taking a Docker file and executing that cookbook, into something called frontend. So essentially, frontend is this new intermediate layer. And what it's responsible for, it's responsible for taking the source code, if it wants to as well, and executing some arbitrary actions on it. So it's no longer tied to just the Docker file. You could potentially have anything that can be executed and expressed as a certain layer, certain directional graph of actions, and you can basically potentially create any form of process to turn your source code into a container image. So that basically gives users much more freedom in terms of what they can do. And there's a number of different front-end implementations kicking about, both for making container images, but also for things like making reproducible builds and so on and so forth. So if you're interested to learn more about how exactly the BuildKit frontend works, then you can click on this link. It's essentially describes and draws the parallels between how BuildKit works and how, for example, a C++ service would be compiled in terms of translation into intermediate layer, producing binaries, spawning tasks from binaries, spawning processes from binaries, and so on and so forth. So if you think about what this means for Buildpacks, that means that potentially there can be some sort of front-end image here that will run the Buildpacks actions and serve as a way to integrate the two. So instead of having the Docker file, you could potentially have something that kicks off the Buildpacks frontend, and then that operates in the same way that the pack CLI would do, where it would execute your build, detect, and so on and so forth stages until it gets a container image as the output. So at this point, you might be wondering, well, what's the point of integrating with BuildKit if there is something like pack already? Well, the benefits that this brings is that there's a much tighter integration. So if you have Docker or Docker Compose, then you can just issue a build command. And what will happen is BuildKit will kick in and execute those actions, execute the Buildpacks frontend, instead of having to break out into a different CLI and then go back into the Docker tooling. It also means that by the virtue of having this integration, Buildpacks potentially can extend its reach from just being potentially a way to just make images for deployment to maybe being a bit closer to developer edit cycle, where it can potentially be a way to make images for development and testing and so on and so forth, because composability of Buildpacks can be used beyond just making production deployment images, right? And that also means that anything that integrates with the Docker world can now also work on Buildpack images as well and Buildpack build process. So there are some common integrations out there that you might have heard about, which is VS Code remote containers. And that's essentially the elevator pitch there is you can develop inside a container with your VS Code editor, or PyCharm remote interpreter, which basically is a similar idea, but for Python, where again, you point your IDE into a container, and that provides you with a production-like environment for your application. Finally, there is a lot of work going on the Docker side to make the integration with various clouds more straightforward. So potentially with something like this, you could, with the Compose integration, you could potentially do something like Docker Compose build, which would use Buildpacks to produce an image, and then you could issue a command which will actually, from your Docker Compose, which will actually just deploy to either Amazon clouds or Azure clouds for you without breaking away again into different toolings or being worried about orchestrating these together. So let's try to have a look at how something like this would actually work. So can someone confirm that they can see a shell? And please let me know if the font size is sufficiently big.
It looks great.
Okay, awesome. Thank you very much. So basically, if you remember from the diagram earlier, there was something called front end. So again, this is just a container image. This one is not particularly optimized. It's quite big, but don't worry about it. It can be smaller. And container, basically what frontend is, it's a container image that exposes a particular interface so that BuildKit knows how to communicate with it. It essentially means that you can use the same workflows that you would normally do for distributing it, and referencing it is also as easy as just saying my frontend image is, and giving it the Docker reference. So we are currently in a folder inside the samples repository from Cloud Native Buildpacks. So let me just quickly show you what's inside there. I think I can just do git status, can't I? So basically, the only thing that we've done is we've added a Docker file. And you might be thinking, well, this is just, nullifies the efforts, because if we have a Docker file, then what's the point? But this is not actually the Docker file that you may be thinking of. So let me just quickly show you what that Docker file actually is. And I'll get VS Code and drop that Docker file for you so that you can see it. So it's apps in Java Maven. Okay, so basically, you can see that this Docker file actually doesn't have much context. It just specifies the name of the builder image. So this is similar to what you would have potentially done if you called pack CLI. You would have given it an image of the builder the name of the builder image to use. And essentially what it's using is this syntax comment. So this is the special comment that basically tells BuildKit that it needs to kick in and treat this build as something different than a Docker file. So this means that you can basically switch the behavior and choose the front end, even though you still have this Docker file, or you can even do some other setups, but this one is probably the one that's easiest to go with. And let me just zoom in as well so that it's visible. So this is what our Docker file is. And if you look back, this exactly matches the name of our container image, which is the front-end container image. Okay, so let's try to build this. So I'm just issuing a docker build command. And for reference, in my daemon, I have the BuildKit enabled. So that's why you can see that BuildKit is kicking in here. If you're familiar with the older Docker build, then you know that the output is quite different. So by seeing a lot of this blue, you can tell that this is actually BuildKit doing its thing. And you can see that what's actually happening is that it detected that this is, yes, there is a Docker file, but it's using a custom frontend now, the cloud native Buildpacks frontend. And you can see that it picked up the builder image, and now it's going through all the steps of the Buildpacks lifecycle. So it's found the sources, it ran the detection, it ran the analyze and restore. Unfortunately, there wasn't much to restore because I'm doing a fresh build just for you. And from that point on, you can see that now it's doing the build. So this will take a few moments. And because this is a Java app, so we can see that the Pacato Java build pack got activated. And what it's currently doing is fetching release of JRE, just so that the application can be assembled to run. And on the output of this, what we will see is that we will have gotten an image, which would be quite similar to what you would get from a pack CLI, but it's slightly different because of not complete conformance to the spec. But essentially, it will be an image that contains the sample Java app from the Cloud Natives repository. So let's give it a few moments until it finishes doing its thing, and then we can run the image and actually see it in action. Okay, so you can see that what it's done now, it has finished the build, and now it's just saving some cache for future rebuilds to be slightly faster. And it's exporting the image now. So it's exported all the layers. Cool. So let's now try to run it. So what I'm doing here now, I'm just running this image, and I'm manually invoking the lifecycle launcher. We'll get into details for why that happens a bit later, but you can see that it appears to be running. And if we go into localhost 8080, you can actually, there we go. You can see that it works. So we are successfully serving the application that was built by Buildpack with the BuildKit frontend. So, but that's not just that. I wanted to also show you an example of the Docker integration. So we mentioned that potentially we can have tighter integrations with something like this. So let's go into another sample example. So this is going to be a Django app. And basically, again, here, there were some changes that were done, but they were quite minor again. So essentially, I'm again adding a Docker file. And you can see that in this case, the Docker file is actually using the Google Container Platform builders. And I also have a small setup. You can see I'm using the Google entry point. So this is basically demonstrating the build-docs functionality. You can see that basically if you are familiar with the way that Google Container Builders are working, then you know that this is a builder. And essentially what this one does, it's translating build-docs into the pack environment variables that get injected into the build environment. And the rest of it is just the VS Code remote containers things. So this one is just a big file that was generated by VS Code to get the remote containers to work. And similarly, this is just the setup for remote containers. So let's try to reopen this in a container and see if this. What I'm expecting to see is that, first of all, this will reload. And what it will do is that it will try to build a container, which again will use the BuildKit frontend. So essentially, we are building a development container using the BuildKit frontend for cloud native Buildpacks. And when it succeeds, what we should be able to see is that we have a VS Code window into that container, which is a Cloud Native Buildpacks build container. A similar functionality here, you can see that there was Docker Compose that was called, and Docker Compose in its regard, delegated the build to the BuildKit frontend, because again, BuildKit is enabled. So this one, again, will take some time. So I think we can come back to it later when we can, in the meantime, discuss how how this is actually implemented and how it actually works. So whilst that's chipping away, let's discuss what we've just seen. So how does the BuildKit work? Essentially, high level, BuildKit, as we've discussed, is a special container image. There are tons of libraries and APIs available in Go to make the development of frontends easier. But strictly speaking, there is nothing special about Go. And there can be a BuildKit frontend in Rust, and there is a Rust library, and any really language that supports gRPC can serve as a way to create a frontend. Go is just easiest because it has lots of libraries available, so you'll find that you don't need to reinvent as many things or re-implement as many things. And gRPC is needed because that's how the frontend communicates with the build daemon. So BuildKit runs as a daemon and communicates with the frontend using gRPC, using std and stdout. And the way that high level the functionality works is that you have a graph, directed graph of action that is get generated, and that is called an LLV. And then that graph gets sent to the daemon, and the daemon executes on that graph. So it executes on that recipe, and that is called usually, or in the code at least, it's referred to as solve. So it solves that graph, and as a result of that, you get a reference. A reference is just basically a pointer to say, hey, your output of your build is here. And usually it's just an image, or it can be multiple images if you're doing a multi-platform build, like if you're doing ARM and Intel build at the same time. So if we were to apply that to the BuildKit world, then you would come up with some graph that looks similar to this. It doesn't cover everything, but it essentially would look something like this. So you have your builder image, which would then be combined with the context and a bunch of inputs. Apart from your source code, there will also be probably cache as an input and some user environment variables, which we've previously seen specified as build args, and some platform environment variables. And then we would run through the classic lifecycle of Buildpacks, where we would find what are the actions that need to be called, see if there is anything to reuse from the previous builds, and then do reuse it if there is anything. And then we perform a build. After we performed a build, we just need to construct the final image, which would be a combination of the runtime image, the launcher, which is what we've seen invoking earlier explicitly, and some metadata along with the layers that actually belong to your application. So these would be
lost.
Oh, I was at the edge of my seat.
No. Yeah.
Yeah.
I was riveted.
I'm concerned that this will ruin my ability to bash on Dockerfile if it's still in Dockerfile.
I don't think it has to be
I
Dockerfile.
know.
Right. I
I'm
mean,
kidding.
I'm working on the Project Toml consumption of it, so it doesn't have to be Dockerfile.
So Docker supports another way of telling it to use a different front end.
Well, yeah, I think that was the syntax level part of the Docker file, but then to any, like, let's say to the Docker daemon or through Docker Compose, you could specify the file, right? So you could just specify a project toml file, and then that project toml file, as long as it has that syntax part at the top, it'll execute this different front end. And that's the part that I was experimenting with and hoping to PR into the POC.
So you'd have to, when you do your Docker build, you have to specify a different, you have to go -f project toml, and the project
Exactly.
toml would need a comment at the top of it. Is that right?
Yeah. So it's clunky, but yeah, it's an alternative if we really wanted it to. Otherwise, the Docker file could essentially look just like a project toml file.
Maybe this is a PR we can make into BuildKit, a slightly different interface. Could the front end match against the files in the directory somehow? Like, could you invert that and so the front end image could decide what the correct file is?
No, at least not from the Docker daemon side, because it
I
calls
mean- I mean upstream. like would that be a way, something we could PR upstream that wouldn't be too BuildPack specific? Like, could the image, the front end image have a label on it that says match against these files? Or something?
Yes, that would be difficult because the front end is defined in the file itself at the
Yeah.
top. So,
I mean, I think anything is possible. It would just require a lot of valid reasoning to why we would be pushing for that direction.
Welcome back, Aaron.
Hello, sorry, my Zoom decided to crash for some reason. I don't know at which point I've gotten broken up, so please do let me know.
Can you go back a slide?
Say again?
The diagram that you showed, I mean, you were somewhere in the middle of reviewing it.
Oh yeah, a slide back in
Okay.
the diagram.
So this one?
Yes.
Okay. I mean, I think by now, actually, has this finished? No, it's not. Okay, let it take then. Okay, so I'll start somewhere halfway then. Okay, so we have a directed graph of actions, which is then solved by the BuildKit daemon, and essentially the output of that, the output of the solution, is a reference, and the reference can be either a single image or multiple images. So if it's multiple images, usually it means that you're doing a cross-platform build, you're doing like an ARM and Intel build at the same time, but a lot of the times you just have a single image as the reference of your output. So essentially, this is how it functions, and the way that high level it would work is that you create this graph and then you send it to the BuildKit daemon to execute it. So that's why gRPC is needed. And if, I don't know, again, if at what point I broke up, so feel free to stop me if I'm repeating myself. That means that any language or any ecosystem that supports gRPC could theoretically be used to implement a custom front end, because it's really nothing special apart from being a container image that communicates with a process over gRPC. So I think, again, I've covered that, but I don't know at what point I broke up. So the challenges of BuildKit are that it's quite Docker-centric in some cases, especially if you're looking for the most seamless integration. You have some sort of metadata file that needs to be the entry point to that world, unless you want to go through the more custom setup, which doesn't work as seamlessly. And that means that there needs to be some sort of metadata file that says, hey, BuildKit, you need to use this front end instead of the default one. The way that people usually treat it, based on the example front ends that I've seen, is that they pick up a metadata file from usually one of their build systems. So for example, if you had a, let's say, Rust project, maybe you would have a special command at the beginning of your cargo.toml, which then can be used as that input metadata file. There were also some talks that potentially, project.toml could work similarly in the world of BuildKit, but we'll see how it's going to work. So another issue is that BuildKit, if you want to go for that workflow of integration, seamless integration, and producing container images, it can be quite boilerplatey. And again, I won't go into the detail because I want to leave more questions, more time for questions. And it has also some interesting ideas about how the cache and sharing of artifacts should work. So for example, for the cache model, BuildKit works by having PC machine-wide or server-wide cache, versus if we look at something like Buildpacks, the caches are basically scoped to your application. So it's quite a big difference. And the sharing of functionality of sharing of binaries is a bit difficult because you can't easily inject some binary from your frontend into the build process. So that makes it a bit harder to share some functionality that you might otherwise want to just mount a magic binary, let's say like, again, for some of the Buildpacks functionality into the target image and just run it. But these are kind of implementation details that as users of Buildpack, you may not necessarily concern yourself with. Finally, the big selling feature of Buildpacks is the ability to replace individual layers. So again, something that BuildKit unfortunately lacks in today. And you can sort of approximate that performance and that experience by basically doing something which would translate into the Dockerfile world as a bunch of multi-stage builds and copy froms. But it's not really the same experience. And again, you wouldn't get that nice feature or nice property of later layers not being invalidated by the previous layer change. So if we go into the challenges of Buildpacks, then I've been focusing mostly as a kind of platform creator because essentially front-end is a platform of sorts. So platform spec is a bit tightly coupled to the Docker daemon in some cases, because it appears to have two modes of operation where you have either a Docker daemon or you have a remote registry, which neither really applies in this case. So hopefully it's something that in the future can evolve and change. Again, we've discussed the cache scoping, so just to reinforce, it's slightly different. And Pack CLI also has much more flexibility in terms of what it offers, because you can basically mount anything from the host, which Docker has been historically quite opposed to. And even with BuildKit, whilst you do have some functionality, it's functionality that is treated as you can mount secrets from the host, but not necessarily any host path, which is what Pack CLI appears to allow. In terms of what can be done in the future, so there is still a few things missing. As you've seen, I had to run the launcher command manually because basically the entry point of the image is not set automatically. So that's something that can be improved. There's also some talks, there was some suggestions on the issue from the community that the ID from project.toml could be potentially used as the way to namespace the caches. So that would be an interesting enhancement to add as well. And there is also some things that don't necessarily affect functionality, but would be good to do for the spec completeness. There's some kind of sanity checks, fail fast checks that can happen. There's timestamps that can be reset for the build reproducibility and so on and so forth. Finally, there might be better integrations, as I've mentioned. If there are potentially additions or changes in the spec, then that means that it might be easier to integrate something like BuildKit or some other platform into Buildpacks. So maybe if the builder image is specified in project.toml, then there is a possible way to start to use that as the metadata file, that single metadata file that can kick off the BuildKit process. If OCI is used more commonly as an interface between the platform and the lifecycle, that means that it might be easier to integrate because, as I mentioned earlier, Buildpacks of today sort of have two modes of operation, and that's either you have a Docker daemon or you have a remote registry. So having something which is sort of less opinionated would make it easier to integrate something like BuildKit frontend into this. And that's pretty much it. I can check whether the VS Code is still chugging away. It might still do. I'm not sure why. I'm sorry. I think it must be because I've lost the connection halfway through. So I'll open the floor to questions, and in the meantime, I can try to get this VS Code thing to work.
So I have some questions around caching. I guess
Sure.
first thing to say is I think this is a great idea. I've talked to Tonis about it a bit. Like I'm 100% sold that we should, kind of at least to replace local builds for sure. Use BuildKit instead of implementing our own parts of the life cycle to do that. I think just even looking at how fast this is, it seems like an improvement from what we have locally for sure. The question I have around caching is specifically, there are environments where builds may happen on different, from different containers or VMs, where we don't want to download the previous image before we do the rebuild, and then upload the layers that changed. We just want to rebuild the layers that changed without having to do that initial pull. And I think there's actually an issue in BuildKit. I'm not sure if you've seen this when it wasn't linked in the presentation, that Tonis actually kind of encouraged us to implement when I had a chat with him. I linked in the Zoom for a merge LB that would let you do builds locally and then not have layers present unless they're accessed, essentially, so that when you can do the push up to the registry, it'll kind of do the same thing our current exporter does, where it doesn't care that the layer isn't present locally when it stitches it together. And so I'm wondering if you've seen that or thought about strategies like, does it, I guess, should we position this as something that is, just an option for local builds, but when you're building against a registry, we keep our current integration? Should we try to implement this first before we roll out BuildKit support and then get rid of the current exporter implementation? I'm kind of curious where people are thinking there.
Can I make sure I'm understanding you? So this merge LB would be for creating basically partial images in the daemon that could then be pushed to the registry.
Exactly.
So then like our registry implementation would go through the daemon first and always be pushed rather than having a publish that works directly against the registry.
Exactly.
I feel like that makes sense to me on some level. Our registry implementation, the way it is now, is probably about as efficient as it could be and as efficient as this would be, because we don't need to recreate layers that don't need to exist. But I think it runs into problems with how users want to use the tool. Most people do not want to just directly build things into the registry. They want to build it locally and then push it. So if we could get the same characteristics without having to, while still doing a local build, that'd be pretty cool.
Yeah, because isn't it my understanding that basically this workflow, this BuildKit workflow, is all making operations within the Docker daemon? So like there is no registry concept, right? It's not like publishing or pushing anything remotely until you do a Docker push. So I basically wonder if they're separate conversations.
Yeah, essentially what you can do from inside BuildKit frontend in terms of accessing the daemon is quite limited. So you don't have the ability to, for example, access the Docker socket or do things like for example, find out what is the tag of the image that you're building. You are supposed to give out a reference, which is basically, here's the contents of an image you asked me to build. And then this is where the rest of the BuildKit daemon takes over and says, okay, I've took the contents, I took the metadata that you produced, I'm going to target as this, maybe I'm going to export it into a tarball, or maybe I'm going to save it in the daemon, or maybe you want to build and push at the same time. So this is where sort of that handover happens, and the front end doesn't participate in those actions anymore.
I have one question based on that about a point you raised, that it would be nice to be able to export to like an OCI layout or tar file. I'm not sure I totally understand how that interacts with BuildKit, sort of based on this, based on that explanation, where it seems like if, like we don't need, from the sounds of it, it doesn't sound to me like we need to build a tarball first and then give it to BuildKit to finish our build. Instead, we're giving a set of instructions to the daemon, then it runs it and ends up with a Docker daemon.
Yeah, so you don't necessarily need to give it a tarball. The difference is that if we look at the way that the life cycle today works, particularly the exporter bit, it has two modes of export. And one is I'm going to export to a Docker daemon, and therefore I need access to Docker socket, or I'm going to export to a registry, and therefore I need registry credentials. So this is the bit that sort of clashes with the BuildKit way of doing things, because for the BuildKit, you just say, here's a file system. It doesn't necessarily need to be even tarballs. It's just you create an image file system, and then BuildKit knows how to export it. So I think the clash that's happening is that BuildKit wants to do its own export when the Cloud Native's platform spec has quite rigid ideas about how the export should function and what are the modes of operation. I hope that made it a bit clearer.
Yeah, I guess I'm not at all surprised that our current spec doesn't account for this, and that we would need to do something different here in order to target BuildKit as an endpoint. I guess I'm like, maybe we don't need to do this all here, but curious to take this offline to learn like in detail how you're sort of creating this file system for the final app image in BuildKit. Because our export step, like right now, the state of the container that's running export isn't the state of the app container. So somehow you have to gather the exact set of layers you want and make it into a file system on top of the run image, right? I'm sort of curious about how that's working in this demo.
Yeah, sure. I mean, we can, if we have time, we can dive into that even now. But if there are other questions, I'm happy to go whichever way.
Well, I think for that file system that gets generated, right, the problem is that BuildKit doesn't let you generate a partial OCI image layout, right? And you have to have the full image that gets exported locally on the file system before it'll do the export. And that's the big feature that's missing comparing our exporter to BuildKit's exporter, right? But it seems like they're open to, a feature in BuildKit that would let you create a partial layout and upload that to the registry. Just from talking to Tonis and reading that particular issue, we may not need our exporter to achieve the same outcome if we're willing to make some contributions upstream, is my understanding.
I think it's worth calling out that when we export to the daemon, we do essentially have to construct the full image.
For sure.
Right
Just
now.
thinking about the registry case. Right?
Just thinking about the registry case. And the registry through BuildKit. So you're saying export to BuildKit. Partial.
So my BuildKit builds some layers, right? As it runs through the LLB. I assume that ends up as OCI on disk at the end, and that gets sent to the registry. But right now, BuildKit has to process and generate all of those layers, right? And it has to come up with a full image before it gets exported to the registry. If instead it was comfortable, like as in that GitHub issue, keeping pointers to layers that aren't actually present through that build process, saying, okay, this is cached, I don't even have this, but in the end, I'm going to write a reference and I'm going to keep an empty reference in that file system based layout I generate, and then upload those layers to the registry. I'm not convinced that this 1131 gets us all the way there. It may just let us do the local build and have those empty references. I'm not sure if Docker would be comfortable. There might be a little more work on top of this to get that working, but it seems like they're open to, implementing that amount of functionality upstream, and that would let us get rid of our, kind of custom logic for, partial image generation that we're doing in the exporter in the end. There's another problem with this though that I was going to bring up, which is that in a lot of the platforms that run our builds, they run without user namespacing, like no capabilities whatsoever. And so in those cases, I think if we tried to do the build during BuildKit, and even if we had that partial export functionality, those platforms would need to give more privileges to their build containers, like if it's Kpack running on K8s, for instance. So that'd be another reason to maybe keep our, direct registry exporter implementation around anyways.
Yeah, I mean, I totally agree with the registry case being something that's supported. I think when Emily and I spoke, we were talking about keeping the registry, the OCI registry implementation, and then replacing the daemon implementation with an OCI layout, right? And then Pack, for instance, could then take the outcome of that OCI layout export and put it into the daemon in a quote unquote efficient manner. And then that would be the same implementation that we could use in BuildKit. Because, I think this might lend into like the code that Eric was about to show, but during the steps that, you create this LLB graph or whatever, during the execution or after the execution of the exporter, like that happens in sequence, right? And so then from there, you could specify the next step, which is to look at the outcome of that OCI layout, whatever the exporter produced, and then use those files to generate your final image that's then referenced outward. I don't know if that helps, but I don't know, Eric, if you want to speak a little bit more to that.
I mean, I can show how it is implemented today. So it's not quite the same, again, efficiency as potentially the Pack CLI does, but essentially you can see here this code, and again, let me zoom in a bit. This is where the export basically procedure begins. So we get the run image, and then we do the export where we add the launcher, add the buildpack launch layers, and you can see basically the operations that mostly happen here is copy. So it copies from the file system that produced the build, and it copies the particular layer that we want to copy. And basically these layers, the way that, again, this happens today is basically just by running solving the LLB, which again gives us the file system, and then looking at the .tomls which were produced and checking whether they are launch layers or not. So basically walking the file system saying, this is a launch layer, I need to copy it. This is not a launch layer, I can skip it. So this is then feeds into this LLB copy operation. And this is what together, when combined with all the other bits like run image, like launcher, like the up layer, produces that output image. So you can see at the end, basically it has an LLB state which has all of this layered on top of each other, and we solve it to get a reference, which then gets used to export an image.
So in this case, the build happens first, generates all the layers, and then when you're doing what you call the export phase is actually running copy instructions to copy all the layers in separately. So it's not like BuildKit is orchestrating the build process itself. BuildKit is just orchestrating the construction of the, like image in the end, right?
Yeah,
it's not
so
taking snapshots after each build pack runs or something, or after the each layer gets generated. Yeah, okay.
Yeah, essentially, so if you think about every box of this graph being an LLB state, basically they all reference each other. So there's a builder state that then gets referenced when it's all combined. Then there is an LLB run operation, which is represents the detect stage. Then we copy any results from that. Then we do analyze, which again, it does a bunch of LLB runs. And then the output of that, when you solve this graph, this middle bit, is a file system, which then, as mentioned, basically you walk through, you can, and this is where the export process that we've just seen happens, where it finds what are the launch layers, what are the layers that need to be included, and so on and so forth. So this is the bit that I had to basically mimic the life cycle in, because again, because of how life cycle operates today. So I had to basically mimic how it works by looking at the launch layers and constructing that file system that BuildKit can understand and can export into a Docker daemon as the image.
So this might be a terrible analogy, but I'm thinking of this along the lines of like futures and promises in JavaScript, right? Where you're just like creating this stream via LLB of like what should happen during these steps. And then when you pass it to solve, it does everything internally, right? So you could put in between these steps or states what you want to happen in those particular instances. Is that a
Yeah, I think
good
that's a
analogy?
really good analogy, because essentially you go through the process, and frontend can either do it once, or it can do it many times, where you make an LLB, you make a graph, you give it to BuildKit to solve, it returns a reference to you, and then you can do something with that reference. So you can either export it, or you can look inside it. You can look at the files inside, you can maybe inspect, read a single file, look through the directories, and so on and so forth. So you can basically chain these. And in this case, there would be two of these cycles that happen, because the first cycle happens for the build. And then this is when the front end inspects the output of the build, says, what are the launch layers? And then the cycle happens again, where an LLB is constructed for that particular build to say, pick this layer, combine it all together into a new reference that then will get exported. So I think promises is actually a very good analogy.
One last
You're
question
doing the
here.
Oh, sorry.
Go ahead,
Go
Joseph.
ahead, Emily. I was just going to ask a simple one. Like these images that you're producing, they don't have the 0 timestamps, do they? Right? Because you're copying it from the built image instead of the tar. I guess that's one piece that the export's probably missing, unless I missed that in the export.
Yeah, so this is something that I mentioned on the future work. I don't see why that couldn't happen, because we do have access to that file system. So conceivably, we can just say, hey, reset all the timestamps.
There are two places where there are timestamps. There's in the files themselves, so we zero the timestamps for all the files on the disk. Then there's also in the image that gets generated, there's like a created at time that we also zero, so that it's possible to rebuild like literally the same, image has the same digest in the registry at the end if you build with the same inputs. I think you're talking about the ones in the file system, but BuildKit also let you zero the timestamp of the image that gets generated.
I
wonder if the
not
LLB
aware of
lets you
that.
do that. Yeah.
You do have access to the metadata, or image config, which is separate from the file system. But I've never tried to actually set that to see if BuildKit would respect it. I would go off on a limb saying that probably BuildKit sets it, because that sort of falls into the whole BuildKit wanted to take care of export story.
So that'd be another feature upstream, is turn off the
One thing I'm curious about is like right now we do things like take what the diff ID of different layers are going to be and like put them in a label in the same image. And with this LLB copy interface, can we get back the digest of the layer from that and then use it in another step to make these labels?
I don't know enough to answer that, because from the interfaces I've seen, you don't seem to get access to the intermediate layers. You only get access to the output. There might be some hidden API somewhere that I'm not aware of.
For the thing you generate for this OCI on disk format you generate, what are the layers tarballs or the layers TGZs? What are you generating directly and then passing to BuildKit? Could we calculate the checksums ahead of time?
I think you're just generating a file system. One
Like
step at a time, right? Like the actual file, the file system of the final image, if I'm understanding this correctly.
So the snapshots, so you see, how do you end up with separate layers for each, like once a build pack runs, it's going to generate, let's say 10 layers, right? How do you separate those into separate things? Is it later you're doing copy instructions on them?
So basically every LLB command you run produces a layer. So you can see here, this is an example of a run command. So this is where we are executing the builder part of the platform. So you can see it's not actually running it. It's, again, coming back to that idea of promises. This is basically just saying, hey, as a part of that graph, what I want you to do is I want you to insert a run operation in there. And this would be then corresponding to this build box over here. So essentially, we would say, hey, I want you to take the file system that I've had before from the previous states, and I want you to execute a run command on top of it. So every single LLB command that you add on top of this would produce a layer. And then when we come round to export, sorry,
I didn't mean to interrupt. Go ahead.
And then when we come back to the export, you can see what we do here is we do the solve. So then the output of that is the build image when we execute on all of those actions, execute on all of those promises. So then again, if you want to get multiple layers out of it, this is where this thing is happening, where basically right now the front end is looking at the build file system and it's looking for individual layers that BuildPack produced, and it basically translates each layer into a separate copy, which then, because it's a separate LLB operation, it then produces a new layer of the image.
So
I feel like you can really see how this came out of Dockerfile. It's like I'm going to do a command, and each command I do is a layer. It's like a programming interface for that kind of.
Yeah.
And the end result is the file system that's been created by all of the commands.
if we wanted the diff IDs back, you know, I'm not sure exactly what context this export's running in, but if this export's running with the files currently on disk, we could just, you know, the diff IDs are uncompressed. So we could stream everything through tar, pre-calculate the diff IDs in the stage, and take a little time.
That's kind of what we do now. We like calculate all of our own diff IDs. Like I was just sort of, this is not a blocker at all. I'm just asking because a lot of the time we spend in export is spent calculating diff IDs. And if we're like doing this step by step against the daemon, if it could somehow, because it's going to recalculate them anyways, if it could somehow just give us that back instead of everyone calculating it twice, it would be a lot faster than it is now.
Do we actually
I think it's why it looks so fast in this demo, because probably nobody's kind of like only the daemon's calculating it. We're not spending time recalculating it.
Yeah, so it's completely reliant on BuildKit there. So that also means that if you were, for example, to run it against the exact same file system, because it knows that the input has not changed, it will just return all cached as well. So yeah, it's not doing anything sort of magic around layers by itself. It defers to BuildKit completely there.
Do we need the diff IDs if we're not going to support like rebuilding from a remote image or something like that? Are those labels really necessary if you're just scoped to rebuilding locally?
We use them for restoring layers, but if we were restoring layers differently in this world, could be different, right? Like you can imagine doing it in this mode I mentioned by like file path. Like you have an image and then you copy the files from that path rather than, pulling a blob out of the registry by diff ID or Docker saving and pulling a blob out by diff ID. You would instead tell BuildKit to copy everything at a path during restore back into your build container.
That makes sense.
All right, so I know we're at time. Are there any last minute questions?
Before we go, I just wanted to also show that VS Code did eventually complete. And if we look inside here, we can see that we have our BuildKit generated file system, and I have VS Code running into it. And I can, for example, see I get all the autocomplete from my application, so on and so forth. I can potentially even run things here if I had the correct path set up and so on and so forth. So this is the bit referencing the integrations that you would potentially also get if you integrate with something like BuildKit.
Awesome. And this is using the Google Builder, is that right?
Yeah, so if you look inside here, let me just zoom in a little bit. You can see that there's Google Python pip, Google Python runtime. So it's Google Containers Buildpacks builder.
Just want to know who's built packs for that slow. I'm just kidding.
Cool, awesome. Well, thank you again, Eric. I think it was a really insightful presentation. I do appreciate it. And yeah, we'll definitely keep working on it. Like I said, I have maybe you dropped off, but I have a PR coming for Project Hummel that hopefully we could collaborate on.
Nice. Yeah, that'd be awesome.
All right, anything else? Cool. Thank you all. See you next time.
Thank you very much. Bye-bye.